Hello, everyone. My name is Sachiyo Tanaka Mukherji. I'm a lecturer at the Department of Environmental Sciences at the University of Houston, Clear Lake. Before I came here, I've been here for about 5-6 years now. And before here, I was at the University of Utah doing some research. I did some 2 postdocs. And I'm going to talk a little bit about what I did at University of Utah, not too much, but what I did was really try to get something out of the waste. And that's something that I'm really interested in. And so Utah, what I did was just basically try to get the fertilizer out of the urine, the human urine. I didn't use the human urine. I had to do a synthetic urine, but there's the chemistry and then the process is comparable. And that's what I did in Utah. And well, I did something else, my research field is like a bioremediation, use of plants to, contaminated soils or groundwater. And that's my PhD, as well as most of my postdoc work, in that direction. But here in the University of Houston, Clear Lake, I focus on teaching, and some of the class that I teach was like a targeting for the non-science students. And those are the students that really these students really not that interested in environmental stuff. So I'm trying hard to make them interested. I hope they learn something out of my lecture, and then maybe if I can impact their life in one way, the other way is great. But it's hard because they're just taking my class just as one check mark, and they just want to get graduate, and so it's kind of hard. So try to make it fun, and then but that's what I do here. I enjoy teaching upper level undergrad course as well as graduate students, graduate courses. These students are much more motivated. They are curious. They want to learn about environmental science, technology, research stuff. So that's really always fun to meet graduate students and upper level undergrad students. Today, I'm really excited because I really believe in the future generations. Who was that? Larissa, I think you said we can't really go into the elementary school or young kids to talk about environment stuff because people say we are doing a brainwashing or something. So I was laughing really hard on that because I do believe that we have to start talking to the younger generation. And elementary school is great because I started interested in environmental science when I was 4th grade. So I think, their brain is flexible and then they're really curious about a lot of stuff. So, but anyway, let me start. And my topic is, like I said, the resource extraction from human and animal waste. Now, I think you all received the document from the Ohio Envirothon, and then it has my chapter. I believe that was chapter 5, and there's like 20-30 pages. And I'm like, it's no way that I cover every materials in like 40-45 minutes presentation. So I try to cover all the materials which was in the document. But of course, I just picked some of the important information I would like to share today. So this is my outline. I'm going to start with the resource recovery introduction. Today, my talk, I'm going to focus on the 3 resources, like a methane and fresh water and nutrients. And I will start with why, okay? And then after that, the human and animal waste. These are the resource that I would like to use to extract a useful resource such as like methane and fresh and nutrients. But how much do we generate and what's really in there? So I'm going to start from that. And then after that, I will just share with you all that some of the examples, like how can you extract nutrients from the human urine, or how can you get the methane and fresh water and the fertilizer out of the sewage, and as well as animal manure, like how can get methane and fertilizer out of manure? Is there any issue associated with the practice? And then I would like to finish with conclusive statement, and then I would like to take some questions. Okay. So organic matter, right? So whenever you hear the organic matter, you go to grocery store and you see these organic sections and you're like, okay, this is organic. Well, these organic fruits and vegetables and meat and fish, word organic, really what meant was like, this product was produced without harmful toxic chemicals. There's no growth hormones, no antibiotics being used. They are not genetically modified. And there are certain criteria the farmers has to follow in order for their products to be called organic. And then once they can sell it at a higher price, and it's good for profit-wise and good for environment, all that stuff. But when I said organic matter, I'm going to use our organic matter, the word organic matter, throughout today's talk. So when I said organic matter in this today's talk, is this, this is organic matter. So like a meat, banana, cupcake, fried chicken, and milk, this is all organic matter. So I'm like, well, there doesn't have to be organically produced or use pesticides or growth hormones, antibiotics, doesn't matter. This is all organic matters. That's what I want to say. And what do you mean by that, right? So the organic matter, this is organic compounds. Organic compounds in the chemical term is that contain carbon and hydrogen bond. Carbon, the element, hydrogen element, carbon, hydrogen bond. That is the definition of organic compounds, right? So let's take a look. Organic compounds contain carbon and hydrogen bond. Sugar, sugar, this is the molecule. One of sugar is glucose. As you can see, there are like carbon, there's a hydrogen. You see the carbon-hydrogen bond. So the sugar is organic compound, so the organic matter. What about the protein? Well, the protein is made of amino acid, and this is just the sum of the amino acids you can see here. And you see a lot of carbon here as well as hydrogen, right? Carbon and hydrogen. So the amino acids are organic compound, and then therefore the protein is an organic compound. And what about fat? Well, the lipids and fats, you see the bunch of carbon and hydrogen. So definitely the organic compound. So you see where I'm heading for. The beef, the fat, the protein, carbohydrate, milk, fat, all these things. Deep fried chicken, protein, banana, sugar, cupcake sugar, oil, butter, all these things. It has a lot of carbon and hydrogen bond in it. And that's why this is called organic compounds. And that's what I call this is organic matter. Okay. Also, the organic matter as well. This is excretes, animal, human excretes, feces and urine. They're organic matter as well. It has a lot of carbon and hydrogen bond. And today's topic, I'm just going to use these organic matter, like, this feces and the urine. What can we get out of it? So that's what I want to talk. Okay. The next topic, the methane, right? I want to talk about the methane. And the methane, and then the fertilizer and the fresh water. So let's start with methane. Well, the methane is the main component of the natural gas. Like 70 to 90% of natural gas, that's methane. Now, the natural gas has a smell. So that's why you can tell when it leaks, if you have a gas leak, you can tell. This is a gas smell, but that's not smell of methane. Methane has no smell, no color, no nothing. So the gas company, they add the substance. That's the smell of gas, but that's not methane smell. But anyway, as you can see from this figure on the bottom, like x-axis is the year, and then y-axis on the left-hand side, that is the annual U.S. electrical power generations. So as you can see that, United States, we heavily depends on the natural gas to generate electricity. 1/3 of our electric energy is from the natural gas. Sure, yes, the natural gas is fairly clean in a sense, like better than coal, but it is still the non-renewable fossil fuel. Now, the question is there any way that we can produce methane from something else, like organic matter? Why not? So the organic matter can be converted to methane under certain conditions. What is the certain conditions? That is called anaerobic condition. No air condition, no oxygen condition, anaerobic conditions. So under anaerobic conditions, the organic matter that I was talking about, chicken, beef, the animal waste, human waste, whatever, organic matter can be converted to methane. Okay, so that's great. Now, this is not something that because we are so smart, you can come up with this. Well, nature does that already. We learn from the nature. So if you go to wetland, rice field, you step on the sediment, you see like a little bubble, formation bubble. And what are they? This is a methane gas. So the methane doesn't dissolve in the water. So if you step on the sediment, there are some methane gases trapped in the sediment pore space, and then that release. So that's methane gas. If you can collect and then lights, it's going to burn. So that's a methane gas. And how that is formed, right? If it's just like the straw. Like if you insert a straw and then hold the top and then you pull it off, you have some water, right? At the bottom. Same way, if you go to the PVC pipe, the clear PVC pipe, and then go to the sediment and then insert in a vertical way and put the cap and then take it out. So you can correct the sediment core samples just like this. Okay, and then the sediment core, the top portions, right? It is exposed to water, so it has some oxygen in it. But as you go deeper, there is not absolutely no interaction with oxygen. So as you go deeper, there is no oxygen. So anaerobic conditions. There you go. So we have a lot of organic matter. It doesn't have to be cow dung or like a human excrete. At the bottom of the sediment, there is like a dead leaves, maybe the very dead fish, dead whatever, microbes, dead whatever. There's a lot of organic matters in the bottom of the sediment, and these will be converted to methane under anaerobic condition because at that deep sediment there is no oxygen. Okay, so we learn from that. Microbes, there is a microbes. The microbes can break down the organic matter to the methane gas under anaerobic conditions. Renewable, right? We have a plenty of waste, the organic waste. So, this is renewable. We can make a methane gas. What we need to do is we just need to create an anaerobic condition and put all these microbes to do the job. So we learn from nature. So that's something that I would like to talk about it today. And the one more things that is the fertilizer, okay, the fertilizer. So the fertilizer, you can see from this figure, the x-axis is year, the y-axis, the primary y-axis, like shown in the green, that is the fertilizer consumption, million tons nutrients, and the right-hand side, the secondary y-axis, that is the world population in a billion. And as you can see that the world population is steadily going up. Today, it's about 7.6 billion people on the Earth. And then it's keep going, and then it was predicted to reach 10 billion by the 2050. So in next, 30 years, we're going to add 2.4 more billion people. That's a lot of people. Now, this wasn't possible. This sudden growth of human population wasn't possible if we didn't have a fertilizer. Okay, so the fertilizer production as well as consumption kicked in around 1950, around that time when we found petroleum, the fossil fuels. Coal was there before, but coal is kind of hard to get. So the oil is easy, you can pump it out. Same for the gas. So it started kicking in. And of course, improve sanitation, hygiene, better medical, better healthcare accessibility, all these things, and then education as well, all played a role in this sudden growth of the world population. But fertilizer, application of fertilizer, that really increased the crop yield dramatically. And that really helped to increase the human population on the earth, right? Let's take a look what is really in the fertilizer. So this is a Miracle Grow you can get from Home Depot or Lowe's, but pretty much it's a whatever. If the farmer doesn't necessarily use the Miracle Grow, but they use the fertilizer, which is pretty much has similar constituents like a Miracle Grow. Now let's take a look at the label, right? It has a total nitrogen in a form of ammonia or urea, and then also phosphorus, and also some potassium, and then you have some minerals at the little trace amount. The majority, so today I want to focus on that, is the nitrogen and the phosphorus, and then we call it plant nutrients, the primary nutrients for the plants as well as algae. The photosynthetic organism, algae, cyanobacteria, they all need nitrogen and phosphorus to grow, to do the job, to the photosynthesis, right? And so, like I said, the synthetic fertilizer really, but how can you produce like a miracle grow, for example? I mean, those nitrogen, like ammonia and urea and phosphorus. How? Phosphorus, you need to go, you need to mine. But what about the nitrogen? Well, we have a lots of nitrogen on the earth. I mean, where are they? Air. Like 78% of air. That's dinitrogen gas. Great. We have a lot of nitrogen. Problem solved. We can just get the somehow the nitrogen gas and then just to convert it to a solid form and then make a fertilizer. Well, the life is not that easy. I mean, plants and algae and including ourselves are very picky. We don't want a dinitrogen gas. We want a different form. We want ammonia. We want a nitrate. We want a nitrite. Different form. We want a urea. We want a organic nitrogen. We cannot use nitrogen gas as our nutrient source. So what do? Well, the nature take care of the problem, right? So the nature, the microbes. I mean, there is the microbes and, the specific type of microbes. They can do this job. They can convert dinitrogen gas, which is inert, which is not available for us to use, any living organisms to use, convert it into the form which can be used by the living organisms, such as like ammonia and nitrate and so on. So the nature took care of it. Great. The thing is, the natural process is slow. I mean, usually slow. And then we need to have a lot faster conversion rate. I mean, this is so slow. And the microbes takes own time to grow. What do? Well, we need to come up with some artificial process, and that is called Haber-Bosch process. Now, the Haber-Bosch process was not really developed just to make fertilizer. It was actually developed during World War One and World War II. That time we need to have a lot of ammunitions like a TNT and RDX and stuff like that. And those ammunitions always have this ammonia or nitrite and nitrate, the fixed nitrogen form. So we had to somehow convert dinitrogen gas to produce ammonia or nitrate so that we can produce more ammunition products. So, that time Haber-Bosch process really introduced, and then but then nitrogen and hydrogen, so the nitrogen gas and hydrogen and converted ammonia. This hydrogen is actually fossil fuel based. So it was actually, produced from the methane gas or some other fossil fuel byproducts. Okay, so this is a fossil fuel dependent process. I mean, you have to have a high temperature environment, you have to have a high pressure environment in order to produce ammonia. Today, we don't really have to make ammunition anymore that much. I mean, we do still, but it's not that anymore. So this process, commercially produced ammonia, 80% of that is actually used to produce the fertilizer, used to make fertilizer today. So the 80% of commercially produced ammonia is used to synthesize, used to make a fertilizer. All right. And the sad news is the other studies show that only 20 to 50% of fertilizer actually applied to crops is used by crops. Okay, so then what happened to 50 to 80%? Those fertilizer, it wasn't used by plants. What would happen? Runoff. Okay, so when you have a precipitation event, you irrigate too much, the soil is saturated, all those ammonia and nitrate and nitrite, they will be washed off with all this rainwater or saturated irrigated water, and then it will taken into the natural water system like creek, river, lake, reservoir, Gulf of Mexico, you name it. You find a way to get into the water system. The consequence is that I'll show you in the next slide. So what we are doing is that we do have a beautiful nitrogen cycle. You guys probably have seen this elsewhere. Like a nitrogen cycle, nature has this beautiful balanced nitrogen cycle. You have a dinitrogen gas, microbes convert it to fixed form. You have a nitrification, denitrification. That's all microbes do that. And then some of the fixed or biologically available form is returned to dinitrogen gas. It's a beautiful closed cycle, the balanced. What we did was the Haber-Bosch artificially using fossil fuel to fix nitrogen or convert nitrogen into the fixed form like ammonia. And we did it so fast that we have too much the nitrogen, the fixed nitrogen, ammonia, nitrate on the soil. So as a result, what happened whenever we have a precipitations, irrigation, the load of all these ammonia, nitrate, which were not used by plants, crops, will find a way to reach a bay like this or river, and then we have this so-called eutrophication problem. Eutrophication can happen naturally, but our activity can induce the rate, promote the rate. So, what happened is, like I said, the nutrients is a food for algae and plants, right? So the algae is so happy. I mean, algae got nitrogen and phosphorus. That's great, a lot of food. So the algae suddenly grow dramatically, like exponentially. But then the thing is the algae is a biological matter. So after some time, it die, right? And then what happened? Well, the dead algae will settle down the bottom, and then it's organic matter going through the decaying process. So during this decaying process, the lot of oxygen in the water is consumed, and then creating no oxygen or lack of oxygen condition, so-called hypoxia. So whenever you see these fish kills in the Galveston Beach or some other lake, that's not because some bad people dumped some toxic chemicals like a PCB to the river or a lake. No, this is just simply lack of oxygen. The oxygen, no oxygen, kill them all. So that's fish kill. And then also it is pretty, it happens in the Gulf of Mexico with so-called dead zone. We have every summer there's a creation. That's because of the Mississippi River carry all the nutrients from the watershed, starting from Iowa, Illinois, you name it, right? All this 1/3 of the United States is feeding into the Mississippi River, those agricultural land. And then those nutrients find a way to get to the Gulf of Mexico, and then eutrophication, hypoxia happens. So we lose a lot of the water area. Otherwise, we could grow, fish and crawfish and oyster and so on, but we can't because no oxygen, everything is dead. So we have that every summer. So what do? We created this unbalanced nitrogen cycle. How can we go back to good, like a restore the healthy nitrogen cycle? Maybe we find alternative way to produce fertilizer. Maybe we can use the waste, like animal waste, human waste. Again, going back to this picture, looks like my favorite picture now. So can we get the nutrients out of it, fertilizer out of it? One more resource I want to talk is that the fresh water. Okay, so the fresh water, plenty. I mean, the water is plenty. We have lots of water on the earth. Like 2/3, 70% of the earth, the land is a water, but those are salty ones. And then how much fresh water we have? Not much. I mean, we don't really have that much. Most of the water that we can use, or we cannot use the most of the fresh water, right? Non-salty ones. It's actually trapped in ice. So we can't really use it. It's in a permafrost form, or it's in a pole, North Pole, South Pole, Antarctica. We can't use it. So how much water do we have? The fresh water for us to consume or to irrigate water or for to use to industrial applications? Less than 1% of the water we have on Earth. Okay, so that's why you can see in this United States, the water stress, it's color coded. The darker the color, these areas are really stressed. What do you mean by stress? Which means that the demand is greater than 40% of available supply. What do you mean by that? Which means that the demand is getting higher and higher, and the supply is having tough time to catching up. So if you remember that the water cycle that you learned from probably elsewhere, that yes, it's a water cycle. It's beautiful cycles, right? So you have evaporation, precipitations, condensation, precipitations, and then some of the water infiltrates through the soil, recharge groundwater, and that's it. The thing is though, what we didn't talk that time is this. This is Ogallala Aquifer. We have this, and this is the largest aquifer we have in the United States. It spans like 7 states, and then of course the Texas, the west side of Texas, we have Ogallala Aquifer as well. And all these agricultural, the farmers, agricultural land, they, Colorado, Nebraska, Kansas, South Dakota, Oklahoma, New Mexico, Texas, farmers, they really depend on the fresh water supply from Ogallala Aquifer. Hydrogeological cycle, water cycle. What we didn't talk was that it's a cycle, but the rate is different. So if we pump, let's say, to irrigate water, right? To irrigate crop, agricultural field, if we pump too fast using a fossil fuel, you pump really fast, the groundwater can be only recharged at very, very slow rate. If you think about it, right? You have a precipitation and then the water has to travel through all those geologic structure. So a lot of soils, a lot of sand, clay, and the water has to go around that. It takes really, really long time. So you're pumping really fast, but then recharge rate is very, very slow. So what happened, right? So you can see this is also color coded. The darker the color, the water ground level is declining at faster rate. So it's not like, it's the water table is changing the same level everywhere. Some places are affected more seriously than others, like Texas, right? For example, Oklahoma, their decline of water table is more serious than like Nebraska and South Dakota and so on. But on average, some data have shown that the net groundwater accumulation rate is negative. Negative means we are losing. Okay, we are losing every year about 2 inches every year. We are losing. So, like I said, some part is greater than this, or other part is less than that. This is just average data, and Ogallala Aquifer is huge. So it's not like 2.16 inch happening everywhere throughout the Ogallala Aquifer. This is just average value, just to give you a guideline. But we do have this freshwater problem. I mean, population is growing. The U.S. population is also growing, mostly because of the immigrations. It is growing just like other part of the world. And so we will need to have enough, we will need to make sure we have enough fresh water for everybody, right? For the future generations. So let's just use wastewater. Why don't we start drinking wastewater? It's like a renewable. I mean, it's not going to go anywhere as long as we have here. We will generate wastewater. So let me into the human waste. So what's in there? The human waste water. I mean, this is like a data from the EPA. How much water do we use at home? On average, this is 2016 data, the end user of water, residential use of water, and the toilet, 24% of toilet water, followed by shower, faucet, clothes, and like laundry, and the others, and leak, 12%. Wow. In fact, right now, I found a leak from the dishwasher yesterday, and it was very sad. I mean, I think it's been leaking for a while. So it does happen, unfortunately. But 12% actually surprised me. The number is quite higher than I expected, but it happened to my house, so maybe probably it's commonly happen. And the wastewater, raw sewage goes to a treatment facility, and then by weight, this is the raw sewage water. It goes to a wastewater treatment facility. 99% by weight. Okay, so by weight, that is water. All right, and then the 0.1%, that's others. What are the others? Those others, the wastewater treatment facility try to remove. Others include, I don't have a complete list of others, but I chose those related to today's topic, which are organic matters in the others. What are the organic matters? Of course, feces from toilet, flush water, urine, sure, toilet paper, why not? Dirt, food, grease, hair, like a cleaning chemical, stuff like that. That's in the others. And then, of course, some microbes. And then the sick people, they excrete pathogens. So you do have some pathogens as well, right? And I want to introduce one parameter that I want you to know. Maybe you already know, but I want to just refresh your memory. The BOD, the biological oxygen demand, BOD. So what is it? Well, I want to know how much resource we have in a wastewater or any type of waste, and that means organic matter. But how can I quantify organic matter? How do I know how much organic matter I have in the samples? Now, all these fancy analytical instruments, we can't use it, not just because they're expensive, just because in order for us to use this type of instruments, we need to know what you are analyzing for. You need to know exact chemical, like a glucose, hexose. You need to know what is it, the type of fat, not just the fat, like a specific the chemical name. We really need to know that it is specific chemical. Otherwise, we cannot use this kind of fancy instruments to measure how much organic matter we have in the wastewater. So we can use this. Why? Because wastewater, I told you, it has a feces, it has a grease, it has a food waste, it has a urine. We have no idea what's in there. So what's the easiest way to sort of get idea about how much organic matter we have in the wastewater? Why not measure the oxygen? That's easy. I mean, there is a probe, right? Oxygen sensor. It's you can get this from Amazon, no problem. As the organic matter decay or the microbes attack organic matter as a food, it has to use oxygen. So let's see, in this closed bottle like this, you put the wastewater and close cap, and there is like an oxygen sensor, DO meter in it. And then day 0, I mean, my dissolved oxygen concentration was like 12 milligram per liter. And then next day, some of the organic matter were eaten by microbes, and therefore some of the oxygen was used. So day 1, I have like 9 milligram per liter. Day 2, I have a 6 milligram per liter, and so on. So you can just track how much oxygen is being used, and you can back calculate how much organic matter I had in the wastewater. So the BOD, biological oxygen demand, or sometimes people call biochemical oxygen demand, that is really to give you idea that how much organic matter we have in the wastewater or waste. Okay, so I'm going to use BOD here and there. So hopefully you know what it is. And just give you how much we generate. This is a Houston Public Works 69th Street wastewater treatment facility. I visited there for the field trip once. This is the largest wastewater utility in Texas, 2.3 million people served. They treat 277 million gallons per day wastewater. 277 million gallons per day. How much is that? Well, just give you an idea, the good sized bass holds 40 gallons. So the million gallons would be 25,000 bass times 277. It's too hard to imagine, but that's a lot of water. So a lot of wastewater has been treated. And then on the average, the organic content is about 400 milligram per liter. It's kind of hard to see how much we have in it. But the organic matter, I mean, we do have a lot of organic matter in the wastewater. And if we can convert that into methane, that's great. However, this is not exactly what we do, so I didn't put in too much information to it. So I'll talk about that in like 2-3 minutes when I talk about how we treat wastewater. But this is just to give you idea about raw sewage water, what's in there. The BOD, we have like those biological, the organic matter, the 110 to 400 milligram per liter. This is an average. You also have a lot of nitrogen, total nitrogen 20 to 85. You have a phosphorus 4 to 15. And that's interesting enough that the urine accounts for 1% of total volume of the wastewater. Wow, only 1% of total volume of wastewater. That is what, 1% of 277 million gallons? That's really little. Of course, I mean, only 1.4 liter of urine people excrete every day, so it has to be very little. Even though it's served like 30,000 residents and so on, it will be little because it will be diluted with toilet water, shower water, kitchen water, and so on. But what's interesting is that the amount of nitrogen in wastewater, like mass, the weight-wise, 80% of nitrogen, 50% of phosphorus, that are from urine. The volume-wise is not that much, but the mass the weight. That's a lot. So, I mean, it adds up a lot of stress on the wastewater treatment facility because of the urine, just a tiny little bit of fraction of a urine in a wastewater. We have to do some extra work to get rid of nitrogen and phosphorus from the wastewater. That can be expensive. Okay, so that's that. And then animal waste. Let's move into the animal waste. So the animal waste, what's in there? Well, this is the beef waste as excreted. So this is 1,000 pounds per 1,000 pound. On average, the cow weigh about 1,200 pounds. I mean, at least that's what I found on the data. So like 1,000 pound is a little less than average cow size, but the moisture content is about 88%. And that cow will produce like solid waste, like, the dung, about 104 pounds per 1,000 pounds a cow. And 88% of that is moisture. And then you do have a BOD, right? You do have a nitrogen, you have a phosphorus, you have a potassium. So you see that? I want you to see that the waste is not like just ooh, dirty. No, I want you to see that waste is also the animal waste, human waste, that is also a resource. It has organic in it. And if we can handle well, those organic can be converted to methane or fertilizer, or wastewater can be converted to fresh water, which we need in the future. What about the chicken, poultry waste? So this is again per 1,000 pounds, which is about 170 to 80, 180 chickens. That's again, it's produced 57 pounds of solid per day. This is per day I'm talking about. Pretty much, a lot of water, but you do have a lot of BOD, nitrogen, phosphorus, and potassium as well. Okay, so with this background information, this is actually background information, I'd like to introduce what I did and what I learned in using these three examples. So the first one, can we use human urine as a fertilizer? Why not, right? So it has a water, this urine has a water, pretty much water, 96%. It has a urea. Urea, what's urea? Urea is this. So as you can see, it has a nitrogen, and it's not a dinitrogen form, not N2. So this is a good form. This is a living organism, can use it. Great. It also has some potassium. It also has a phosphate. Everyone produces 1.4 liter. So population grows. We will have always constant supply of urine, which means constant supply of urea and phosphorus, the nutrients. Sounds great. And like I said, why not? I mean, in fact, that we, in Asia or even some European countries, they've been doing that. I mean, historically, they've been doing that. It's like they knew the urine can be applied as a soil supplement or fertilizer. And back in the 16th century, 17th century, they were doing it. And then that was great. That was working perfectly fine. The thing is, though, today we know more than just urine. Our technology has improved, our science has improved, we have more information about what's in the urine, and all that stuff really kind of stop us to directly use urine as a fertilizer. So what's the problem? What do we do? So first of all, if your toilet, if your house is, your wastewater is going to a centralized wastewater treatment facility, your toilet, you don't probably have this kind of toilet. I'd be surprised if your toilet can have this. That's great. This is to the urine separation toilet. So the urine goes to this hole, and then the feces can go to there. So you can collect it differently. And then, so this is great. I mean, your urine is, you can use urine as a nutrients resource, and then solid as a methane or fertilizer resource. That's great. But most of the houses don't have this. It's going to be very expensive to install this kind of a toilet to everyone. The presence of micropollutants, we start to understand that we have a lot of unwanted matters in the urine as well. Not just the urea, not just the phosphorus, not just all those beautiful minerals. We have something we don't want to be there, such as like a pharmaceutical products. I mean, we take Advil, Tylenol, caffeine. It's all in there. Natural hormones, women, men, they excrete hormones. Antibiotic resistance gene, that's another problem recently, like antibiotics, right? People take antibiotics. Some people just unused antibiotics, they throw in a dustbin and goes to landfill and all this thing. And we found antibiotics in the wastewater. And so What I mean by that, if you have antibiotic, the chemical in the environment, the microbes don't like that. And the microbes, have natural mutation, their survival mechanism kicking. They will somehow randomly get this antibiotic resistant gene. And what happened is the microbe itself may be killed by heat, maybe chlorine, maybe, ozone, UV. Well, I would say maybe heat. Let's just be, microbe itself may be able to be killed easily. But this gene, antibiotic resistant gene, this is a piece of DNA that's very robust. That's very resistant to, more robust than the microbe itself. So that can stay in an environment for a longer period of time, even though the microbe itself is not there. So what's the problem? But this gene can be transferred to other microbes which happen to be there. And then the other microbes can gain antibiotic resistance. And what if those are the pathogen? And then what if the humans infected with the pathogen? What if the animals infected with the pathogen? The antibiotic medicine we have, it's not going to work because they gain antibiotic resistance. All this information we started to learn, like urine has this, feces has this. What do we do? And of course, the pathogens, Salmonella, E. coli, all these things, the toxic pathogens, the make you sick, that's also excreted with urine and feces. Now, there's some study in Switzerland, and they asked like 467 Swiss farmers, and they asked like, what do you think of using urine-based fertilizer? And 57% of farmers say like, oh, that's great. I'm interested, and that sounds like a great idea. Great. But then the 30% of them say like, I'm a little concerned about the effect of micropollutants in the urine on my crops if I'm going to use this, right? And that makes sense. I mean, natural hormones, antibiotics, antibiotic resistance genes, some other Tylenol, Advil, you name it. How's that going to have an effect on your crops? Pollution transfer, that's something that we want to avoid. So that's the 30% of farmers share that concern. So now the human urine as a fertilizer. Sure, the easiest way is that just the storage, just store for weeks and months. And then just like that, it been done in many places in the United States, maybe, and then also in some parts of the world. Easy peasy, just to store it. And what would happen? The chemistry will take care of it, right? To kill the pathogen. As shown in this flow chart, you have a urea in the urine we talked about, and then there's again a microbes. The microbes have some certain enzyme or protein, and it will chop off the urine and produce ammonia. And then this reaction results in increase in the pH of stored urine solution to 9. 9 is pretty high. A lot of microbes are very, very picky about the range of pH that they can live. So the 9 can kill or inactivate many or most of the pathogen. So that's great. Just storing a urine, just like that for weeks and months, you can kill them. I mean, you are free. You can have the urine or fertilizer, urine-based fertilizer, free from pathogen. Great. What about micropollutants? What about antibiotic resistant genes? I'll talk in the next slide. Or instead of storing, because you need a lot of space, why can't you extract nutrients? Since urine has a nitrogen, urine has a phosphorus, urine doesn't really have a magnesium, but magnesium salt is very cheap salt, so you can add that into the mixture, and then in a certain ratio, and then you can form the chemical, the white powder. It's called struvite. The struvite is the effective fertilizer, slow releasing fertilizer. Okay, so yeah, sure. I mean, we can do this way as well. Now, the struvite, great, but the struvite has a micropollutant. The struvite has an antibiotic resistant gene. So yeah, I mean, we have to answer this, right? The farmers are concerned about it. They want to use fertilizer, urine-based fertilizer, but they don't want to have micropollutants in it. So a lot of studies going on in that direction. And the first one is the work that I've done in the University of Utah with some PhD students. that we form some strobite, and then we throw some human hormones to the urine, and then from the urine we form the strobite, and then we analyze if those are human hormones. This is a female hormone, by the way, the 17 beta estradiol. This is a women hormones, and if we can, the strobite will contain these hormones or not. And the good news is hardly any or zero the hormones was detected in the strobite. So we could say that, okay, that at least for the hormones, the strobite is free from it. So you can, use a strobite. You have to worry about the hormone transfer from the fertilizer to crops and crops to the environment, that's that kind of stuff. And what about the urine storage? Okay, so I don't know about the hormones. When I did, the hormones are degraded during the urine storage experiment. But then somebody looked into the antibiotic resistant genes, the fate in the urine storage. And the good news is, yes, the increased pH was able to kill the pathogens, but also this robust DNA, the piece of DNA information that's called antibiotic resistance. This particular gene was also degraded in a much smaller pieces to the extent that no longer can be, like a transfer to any other species. So this is just maybe later. This is the idea of a gene transfer that I'm trying to share with trying to talk is that like a bacteria because of this antibiotic random pressure, it can gain some antibiotic resistant genes, the red portions, and then bacteria itself may be killed because of the high pH treatment or some heat treatment or whatever the reason, right? But gene is much more robust, so the gene can remain in the environment for a longer period of time. And the gene can be transferred to other bacteria. And then other bacteria is just great. This trait is amazing. I mean, we are not going to be affected by antibiotics in the environment. So this is something that we don't want to have. We don't want this to happen. I mean, gene transfer, the antibiotic resistance is transferred from one to the other. And then so we don't want to really introduce antibiotic resistant gene to the environment. And luckily, during a urine storage, the antibiotic resistant genes were breaking into the smaller pieces, broke down, and to the extent that no longer can be transferred. Even transferred, it doesn't do anything. So that was great news. Okay, so sure, why not? We can use urine as a fertilizer. Maybe you can use as it is, or you can extract in the form of a strobite.
I got a question on the strobite. How recent is that? Because I've just started seeing that pop up everywhere.
It's old.
Okay.
Yes, it's very old. And in fact, we can produce strobite in controlled manner, but strobite is formed like also in non-controlled ways. Like, for example, a lot of water contains nitrogen, phosphorus, and then if you have some magnesium, it will spontaneously form. And sometimes it's clog the pipe. So it's really is problematic if it has happened in the like the wastewater pipe system or the distribution system. If this strobite is formed, the engineer has to go there and remove it. So previously, strobite formation in the wastewater treatment facility was not really well accepted. Because of that, it's more like a problem than good. But today, I think more and more people realize, like, wait a minute, this is actually a good fertilizer alternative. So maybe that's why you start seeing a paper on that. But most of all these topics that I plan to share, it's all like nothing really new about it. It's just like we didn't have to really look into that because we had cheap alternatives, which is like natural gas and fossil fuel and stuff like that. So we didn't really have to look into that. But now, and we had plenty of fresh water, we had plenty of natural, nutrients. But now we are in a different stage, so we revisit and then we try to optimize it. And so maybe that's why you start seeing a paper lately.
Yeah, the fact that it's a usable as opposed to an issue, like you said. So like, hey,
Yeah.
we got this issue. It's like, well, we can actually use that, and then finding out
Exactly.
how we can actually help make it happen faster now.
Exactly. So, and then also one thing we need to be, there are not much work done is like this, the micropollutants co-extraction. So we want to grade, I mean, this is like ammonia and phosphorus and magnesium, the mixture, but all these micropollutants can be also co-precipitated out. And if that happens, that's not good because when you apply, when you use this turbide and then you spread on the crops, and then if there is a micropollutants, that's bad, right? So a lot of researchers looking into that. I mean, what's going to be a co-precipitated with turbide? That's something that we definitely want to make sure. Antibiotic resistant gene is something like a compost is great. We can get, like a soil supplement from the waste. That's great. But then like some researcher pointed out, well, I found antibiotic resistant gene in a compost. And people are like, oh, that's not good. Because if you find it and then you can spread the bad genes to other bacteria, and that's like, it's very bad for many reasons. And now that's many studies look into that. Hey, don't worry, it can be degraded and so on and so forth. So there are a lot of papers related to that field as well. But anyway,
I think you just kind of proved that one topic for environmental science relates to every aspect. Because it just went from one place to another. You just showed the connectivity, and that's what environmental science is. It's all connected.
Absolutely. Yeah,
So
it's
great job.
all
Thank you.
connected.
I like to continue from example two. Can we generate energy, fertilizer, and fresh water from sewage? Yesterday, after my talk, Mr. Shannon Miftari from Gulf of Authority explained in detail how the wastewater, sewage water is treated at the Gulf of Authority. I had some information about it too, but I'm going to go very quickly because it's going to be repeated information for you. So I will try to extract methane gas and fertilizer as well as the fresh water from the wastewater. This is the process schematic for the Central Valley Water Reclamation Facility at the Salt Lake City. You have primary treatment, you have a secondary treatment, which was explained by Mr. Shano Miftari in detail. And then also it does have a sludge treatment. After the secondary treatment process, you have pretty clear water. This is the third in from the left. That's the after the secondary treatment process. It goes to disinfection and it will be discharged to the receiving water body. In this case, Middle Creek. The sludge treatment will combine all the sludge from the sedimentation tank and the primary treatment and secondary treatment process, mostly biomass, the biological matter, the microbes, and that's the dewatered and goes to anaerobic engineered system. We call it anaerobic digester. This is a primary treatment. It removes settlable and floatable solids, which were explained yesterday in detail. So I'm just going to go quickly. This is a secondary treatment. This is mainly to remove BOD, dissolved organic matter, and it's done by microbes, bacteria. The aeration tank, where the aerobic degradation happens by microbes, followed by sedimentation tank, where the microbes and then the water are separated by gravity. The bottom, we call it the biosludge because it's biological matter mostly, which is mostly microbes, which worked in the aerobic tank, converting organic matter to carbon dioxide. Some of the biosludge is returned to the aerobic tank, and then but some will be taken to sludge treatment. The water is disinfected through UV chlorinated chemicals, ozone, and the pathogens and the microbes are inactivated, and then the water is returned to receiving water, the river. So can we produce drinking water from sewage? Yes, we can. And in fact, it is happening in a space station, the International Space Station, where the freshwater supply is extremely limited. And then also Singapore, also they experienced the freshwater shortage. So they've been doing it and they are providing a free water bottle, which has the reclaimed water produced from the sewage. We have a reclaimed wastewater facility at the Texas, which the Mr. Shannon Miftari also mentioned. That's West Texas, Odessa, and Snyder. That's Colorado River Municipal Water District. So they collect the sewage from the resident and then goes through primary treatment, secondary treatment, and then it goes through advanced process, which is the different type of the filtration process, membrane filtration, reverse osmosis, followed by UV disinfections. And the treated water in this way, which basically the left is before the advanced filtration, the right is like after the advanced filtration system. Basically, everything is removed. Ions, small compounds, virus, bacteria, everything is removed. And this water will be mixed with the raw water reservoir, and then that goes to a drinking water treatment facility to produce the drinking water for the West Texas, which is about 600,000 Texans. Reclaimed water that went through advanced filtration treatment that can be recharged to groundwater, that can be used for the industrial process or to irrigate crops or to add it to the drinking water supply reservoir. The solid, the biomass, which is mostly microbes, so that can be used to generate the methane gas in an anaerobic digester, which is just like a wetland I showed the picture earlier. So the nature does that. So we were creating engineered system just like this. This is anaerobic environment. So there is no oxygen and there is a bacteria in it in this reactor tank. And the dewatered biosludge going to this reactor. And biosludge is nothing but organic matter. And then that's going to be converted to methane. Methane doesn't dissolve in the water, so you can collect the methane gas from the top. It's not just 100% methane, it has some other impurities, such as like a carbon dioxide and also rotten smell gas, hydrogen sulfide. So those unwanted gas will be removed, and purified gas can be used to, sell the electrical utilities or use as a fuel to for the on-site generator to generate electricity and so on. This is a biological reactor, so it will have its own biomass waste, and that's going to go to compost treatment. So try to achieve the zero waste at this facility so that the sludge waste from anaerobic digester will be composted. The sludge biomass is dewatered mixed with wood chips, and that is to adjust the carbon and nitrogen ratio so that you can have a very good quality of compost, the final compost. Composting process is aerobic process, which means the oxygen needs to be provided or air has to be provided. During a process, you can see the steam is coming up. Steam is because inside of this pile, the quite high temperature is achieved. As you can see, within a 10 to 20 days, temperature can go as high as 60 and above degrees C. And that's because as organic matter breaking down by microbes, it will release heat. This is exothermic reaction, and which is very, very important to sanitize, to kill the pathogen which you may have in the biosolids, as well as the compost will be used as a soil supplement. So you may have some the weed seed, and that's unwanted matter. So that can be inactivated by the heat treatment in a compost. Some people are looking into that to try to install the heat exchanger to utilize that heat generated in the compost pile and to heat the water. Right, so that's something that again we are trying to look into that in the zero waste generation. So any energy in any form, we try to capture and then try to use it efficiently. A sewage treatment system, that is some house on-site treatment facility. It's getting pretty common in Texas because the population is going up in Texas. They are building a lot of homes. those new homes may not be connected to the central wastewater treatment facility. So 20% of new homes built in Texas have this OSSF. The way it works is that the black water, gray water mixture get into the septic tank, which were installed underground. And then by gravity, the solid settle down, create the sludge. And then the water, liquid portions will be released slowly to the drain field. And the bacteria will degrade or break down organics. Also, the soil layer, the soil particles will absorb some of the organics and matter in that wastewater. There are the different state, different county has a different requirement for the septic tank capacity, soil texture, distance to groundwater, tank size, and holding time. So you may want to check if you need to install the septic tank at your house. After some time, the solid will be removed. 50% will be biodegraded by microbes in the septic tank, but there will be some remaining solid. So that needs to be physically removed and taken into disposed appropriately. The sewage treatment system, we can also have that like install urine separating toilet just like this, and urine can be collected in a separate tank. The feces can be collected in a different tank like septic tank. Urine is a lot cleaner, the septic tank. Urine doesn't have a pathogen. Urine is a steroid, so urine can be stored in a different tank, and then that can be used as a fertilizer after storing for weeks and so on. Septic tank, we talked about it. So that's something that it's easily, as long as you can install this urine separate toilet tank, you can have a smaller septic tank capacity because urine, you have a separate tank for urine. So this is something that easily we can adapt. And also the septic tank sludge, the sludge may be collected and then can be used to produce compost, or if it's in a community base, we can even have a digester, community-based anaerobic digester to generate methane gas. The animal waste, I shared this table with you before. So it's the per 1,000 pounds of animal, the cow or beef in this case, it produces about 104 pounds of solid waste, I mean the feces per day. And then mostly water, how close to 90% is water, but it does have organic content and some nutrients as well. Usually the animal waste is managed like collecting solid manure and then de-water using this mechanical separation devices just like this. If you have some remaining solid, you would flush with water and you produce liquid manure. Liquid manure by definition is that it contains less than 5% solid waste. And liquid manure can be stored in a lagoon like this or other engineered containments. And then after some times, you can use as a soil amendment. The solid parts of the manure after dewatering treatment, the solid part of the manure can be also applied as a soil amendment. The animal waste, how can we recover energy? You can probably guess it has a BOD in the feces. So you can do compost, you can do anaerobic digester per farm. If you are a mid-sized farm, you can do this. I'll give you an example that the many farmers in California, actually they are increasing their profit by constructing their on-site anaerobic digester. And then also the liquid portion, you can keep it liquid waste. You can keep it in a lagoon and then use for the land applications. Okay, so this is an example what's worth more, a cow's milk or its poop. So this is example for the per 2,000 cow dairy. So the 2,000 cow, so the mid-size farmers, and then the digester maintenance. So they install the anaerobic digester, and every year per cow, they need to pay about $294. Energy generation because of this process, which is per cow, is about 69. Now, if you do the math, it's a minus for farmers. Why would farmer want to do this? Well, the California has incentive under low carbon fuel standard. So based on the energy generated at this particular farm, they get $1,935 per year of incentive per cow. So if you do the math, this is actually a quite jump in their profit. The author said that some of the farms actually their profits increased by 50%. So this is really interesting because if you remember, CH4, the methane gas, is the greenhouse gas as well. It is the main component of natural gas, but this is also greenhouse gas. So if we can capture, that's great. We certainly don't want to emit methane into the air. Now the cow, the cow dungs definitely has a BOD. That's why we can convert it from the solid waste and generate methane. But the cow has this rumen. It doesn't have a stomach. It has a rumen. And then the ruminant, those animals called the ruminants, just like a sheep and cow. Ruminants, they produce their food in the rumen. Their food is converted to methane gas or some other gas, CO2. And then the methane gas, like I said, doesn't dissolve in the water, so the cow needs to expel the gas. So the gas, like I said, the CO2 and methane, and the methane content is quite high. So the up to 500 liter methane per day per cow, that's quite a bit. Okay. So if you do this math, this trend that I just mentioned in the previous slide, that the California farmer, they may consider increasing the number of cows in their farm. Why? Because they can increase the economical profits through the California incentive, right? Which is not good because if you increase the number of cows, you also increase methane emission from cows because of these cows are ruminants. So we are trying to cut down the carbon emissions, and then we are trying to diversify the energy source, and that's why we are looking into the solid waste, the car dungs, the the animal waste, to as a source to generate the energy. But because of this high incentive from California, the farmers they consider increasing number of cows, and therefore they can increase the carbon, the CH4 emission because they are ruminants. So this is like something that we really need to think about it. Conclusions, the human and animal waste. So they have a lot of BOD, so we can generate the methane gas in compost, fertilizer, and fresh water. In these examples, you also saw that there are a lot of benefits to the environment. Reduce natural gas demand because we are generating methane gas from the biomass, which is positive effect on the carbon cycle. Reduce demand for the synthetic fertilizer because we can produce compost and fertilizer from animal and human waste, which is good for the nitrogen cycle. Because of Haber-Bosch process, our nitrogen cycle is very stressed and imbalanced. But by cutting down the demand for the synthetic fertilizer and increasing organic fertilizer, it is a positive effect. It has a positive effect on the nitrogen cycle. And also reduce freshwater stress because we can generate fresh water from our human wastewater. That's the end of today's talk. If you have a questions, please email me at mukherji@usc.edu. I'll try to get back to you as soon as possible. I hope your students will do great on that Envirothon competition. Thank you.